I'm going to show you how to download PhET simulations. And so open up a browser and click on the chemistry button and then scroll down to build an atom. Download. Select the icon that says symbol. And here's the opening window. Well, let's talk a little bit about this PhET simulation. The PhET initiative was started by Nobel laureate Carl Wieman in 2002. And this was done at the University of Colorado, Boulder. The project creates free interactive math and science simulations, and they're very helpful. All right, so now that we're here at the opening screen, let's define a few terms before we get to work on the simulation. First of all, an element is a substance that contains only one type of atom. And so we're going to get a little circular here. An atom is the smallest possible portion of an element. A component of an atom that is smaller than that atom is called a subatomic particle. So let's focus on that term, subatomic particle. The three major types of subatomic particles are shown right here in these buckets. They are protons, neutrons, and electrons. Before we get started working, let's commit to memory a couple of facts or write this down. A proton has a positive 1 electrical charge. A neutron is neutral, and that means it doesn't have an electrical charge. And an electron has a -1 electrical charge. Protons and electrons have equal but opposite charge. Again, a proton has a positive 1 charge, and an electron has a -1 charge. Before we get started, let's make sure that all of the choices in the show box are clicked. We will be able to see the element symbols, whether or not the species that we build, the particles that we build, are neutral or charged, and if they're charged, we'll call them ions. And we also want to see if the particles that we build are stable or unstable. Let's begin by moving one proton from the bucket and into the central space right here, and we're going to call that space the nucleus, this center space right here. So let's see what it is that we built here. Notice that the particle is called hydrogen. It has one proton, and that's in its nucleus. It doesn't have any electrons, so no electrons, and it has no neutrons. Let's take a look at the symbol over here. We see a capital H, and that's the symbolization for hydrogen. And we see a subscripted 1 over here. Notice that this 1 is orange, just like that proton. And so the subscripted 1 tells us the number of protons that there are in the particle. And then we have a superscripted 1 on the left-hand side, and this 1 is called the mass number. The mass number, it's the sum of the protons and the neutrons in the particle. And so this particle has no neutrons, it only has one proton, and therefore its mass number is 1. Then the superscripted number off to the right is the charge on the particle. And so here we only have the one proton. The charge on a proton is +1. We don't have any electrons, and so the charge on this particle is +1. And notice that this particle is called an ion, and this ion in particular has a positive charge, so it's a positive ion. Positive ions are called cations. And so this is a hydrogen cation. An ion is a species in which the number of protons and the number of electrons is not equal. In this case, the number of protons is greater than the number of electrons because there's only one proton and there are no electrons. And so we have a positively charged ion, and it's called a cation, the hydrogen cation. The hydrogen cation is also called a proton. You'll deal with protons quite a bit when we get to acids and bases. Now, let's add an electron to this cation. Notice I tried to put the electron in the nucleus with the proton, and it would not go there. So let's see what this new particle is that we built. It's called an atom. Okay, and it's neutral. And again, a proton has a +1 charge and an electron has a -1 charge. And so if you have an equal number of protons and electrons, the charge on the species will be 0. This type of symbolization that we're looking at right here is called nuclear chemistry symbolization. What a nuclear chemistry symbolization shows is the atomic symbol, the atomic number, as the subscript on the left-hand side tells us the number of protons in the particle, and then the superscripted mass number on the upper left-hand side indicates the sum of the protons and the neutrons, and then the superscripted charge on the right-hand side indicates the charge on the particle. If it's 0, that means that there's an equal number of protons and electrons in the particle. If it's positive, that means there are more protons in the particle than there are electrons. If it's negative, that means that there are more electrons in the particle than there are protons. The superscripted number is black. It is not orange like the proton because now the number of protons and the number of electrons is equal. So we have a neutral species, and it's called an atom. Atoms are always electrically neutral. That is, always an atom will have an equal number of protons and electrons. The number of protons that an atom has is called the atomic number of that atom. An element is identified by the number of protons its atoms have. For example, any atom with 1 proton is a hydrogen atom. Any atom with 2 protons is a helium atom. Any atom with 3 protons is a lithium atom. The 2 models that we've built so far were built using the Niels Bohr solar system model of the atom, which is also called the planetary model of the atom. It's an overly simplified model, but it's very useful. The opposite of that would be a cloud model. And so here the proton is at the center in the nucleus. The cloud that you see there is a map of all the possible places that that electron can be around that nucleus. So we're going to work in the Niels Bohr planetary model. And in this model, the blue dashes, these 2 concentric circles that we see here, they represent orbits that the electron travels in around the nucleus of the atom. So this would be the first orbit, and this would be the second orbit, and the typical terms that these are called are energy levels. So this would be, the inner circle is the first energy level, and the outer circle is the second energy level. An electron that is in the first energy level has less energy than an electron that is in the second energy level. So this portion that is in the center, again, we call that the nucleus. And the particles that are in the nucleus, we call them nucleons. Nucleons. And so the proton is an example of a nucleon. A neutron is also an example of a nucleon. Again, the major nucleons are protons and neutrons. Like the Earth orbiting around the sun, an electron orbits around the nucleus of an atom. And so again, the dashed circles, they represent orbits or energy levels that the electrons travel in as they circle or orbit around the nucleus. An electron is held in orbit by its attraction to the proton or the protons that are in the nucleus of the atom. This parallels how gravity, the pull of gravity, holds the Earth in orbit around our sun. Most of a solar system is empty space. Likewise, most of an atom is empty space. The distances of electrons from the nuclei of their atoms can be visualized as being comparable to the distances of planets from their suns. We already know that if we take this electron away, if we remove this electron from the hydrogen atom, we'll get the hydrogen cation. But let's see what we get if we add another electron. Notice that electron went into the first energy level or the first orbit. It did not go into the second orbit. Now notice we've created a new species here, and this new species is still hydrogen. It has one proton. That's what makes it hydrogen. Let's take a look at the symbolization, the nuclear chemistry symbolization for this new particle that we've built. It has one proton, so that orange 1 is orange like the proton, and that's the atomic number, so it's hydrogen. And the mass number is still 1, so we have just that one proton, we have no neutrons. But now look at this blue number over here. It's blue like the electron. In this species, this particle, the -1 charge indicates that there is one more electron than there is proton. So let's take a look. -1, -1, and +1. So -2 coming from our electrons plus 1 coming from that proton add up to -1. This species is not an atom because it's charged. It's an ion. Remember that ions are a species in which the number of protons is not equal to the number of electrons. And if the number of protons is greater than the number of electrons, then you have a positive ion called a cation. But in this case, the number of electrons is greater than the number of protons, and so we have a negative ion called an anion, spelled A-N-I-O-N. The hydrogen anion is called hydride, H-Y-D-R-I-D-E, hydride. Let's recreate our hydrogen atom by removing one of the hydride electrons. So now let's take a look and see what happens if we add a neutron. Notice this is still hydrogen. This hydrogen has a proton, a neutron, and an electron, so it's still a hydrogen atom. It's a neutral hydrogen atom. Let's look at its nuclear chemistry symbolization. It has one proton, and therefore it's still hydrogen. It has a mass number of 2, and the mass number is the sum of the protons and the neutrons. And so we have one proton and one neutron, therefore the mass number is 2. And then let's look at our charge. It's black, it's not orange like the proton, and it's not blue like the electron, and so we have a neutral species here, a neutral particle. But this atom of hydrogen is different from the first atom of hydrogen that we built in that this version of hydrogen has a neutron, whereas the initial one that we built did not. And so the relationship of these two different types of hydrogen atoms to one another, we say that they are isotopes of one another. So our hydrogen without a neutron, it's still hydrogen, and then we had a hydrogen with a neutron. The name of the hydrogen that has one neutron is deuterium. D-E-U-T-E-R-I-U-M. Deuterium, and it's also called heavy hydrogen. However, the majority of hydrogen that we find in nature is hydrogen with no neutron. This form of hydrogen is called protium, P-R-O-T-I-U-M, protium, and it is the most abundant form of hydrogen in nature. There are two natural forms of hydrogen. They are protium, and the other natural form is deuterium. The natural abundance of protium is 99.985%. So 99.985% of all of the hydrogen that we find in nature is protium. It's the protium isotope. The natural abundance of deuterium is 0.015%. Very, very small. And to put that in another perspective, for every 6,666 atoms of hydrogen that you find in nature, only one of them will be a deuterium atom. On the other hand, for every 6,666 atoms of hydrogen that you find in nature, 6,665 of them will be protium atoms. Again, protium and deuterium are the two natural isotopes of hydrogen. And when we talk about their percentages in nature, we are talking about their natural abundances. So that's a good term to be familiar with, natural abundance. To be particles of the same element, two particles must have the same number of protons. To be atoms of the same element, two particles must have the same number of protons and the same number of electrons. Just as the protium isotope can form a cation, so can deuterium. If we take away this electron from the deuterium atom, we'll have a deuterium cation. So notice it's an ion. It's still hydrogen. It has one neutron and one proton. What makes it hydrogen is that one proton. If we look over here, we see the symbols for it. The atomic number is 1, the mass number is 2, and the charge is +1. Deuterium can also have an anion. So let's add 2 electrons to it. That's the deuterium atom. And notice that that 1 electron went into the first energy level. So now let's add a second electron. And notice that that second electron also went into the first energy level. This is a deuterium anion. We've got 2 electrons and 1 proton, therefore we have a -1 charge. And so again, this is an ion, and a negative ion is called an anion. I'm going to clear out the screen and make yet another form of hydrogen, and I'm going to use this button over here just so that you'll know how it's used. All right, so that takes us back to a clean slate. When we click the button, it took the check out of our stable, unstable box. I'm going to put that check mark back in there. Now I'm going to build another form of hydrogen. In order to be hydrogen, it has to have one proton. So there's a protium atom. One proton, one electron. Now I'm going to add a neutron. So now we have deuterium, or heavy hydrogen. Now I'm going to add a second neutron. And as you can see, this new particle is unstable. And that means it's radioactive, and it will spontaneously decay. This new particle is still hydrogen, but this isotope of hydrogen, in which we have two neutrons and a mass number of 3. So 2 neutrons, 1 proton, the mass number is 3. It's still hydrogen because there is only 1 proton. And it's an atom because the number of protons and electrons is equal. However, it's not protium, it's not deuterium, it's tritium. Tritium. Again, that's tritium. And tritium is not found in nature. Tritium is man-made. Now there is a little issue here. This is a great simulator. However, we can build some atoms that don't exist, or some species that don't exist, particles that don't exist. For example, although I can build it, there is no form of hydrogen that has a -2 charge. Okay, so I built this with the simulator, a hydrogen with a -2 charge, but this does not exist. So the lesson there is that with this simulator, we can build some things that don't exist. You're only being asked to build species that actually exist.